All right, so today I'm going to be doing vectors, topic 4. And in order to start that, we have to first look at what a scalar is so we can sort of go up that ladder of how, I guess, complex it is. So first, for a scalar, we have a quantity that has a size but no direction. Basically, what this means is it's a distance. So we have, let's say you have one car over here. That's a car, and another car over here. The distance between them, let's say, is just 5 meters. That's the distance. No direction or anything, just how far they are from each other. Examples of this include temperature, the mass, volume, and then distance, because it's something that has a size but no direction. And then what we have now are what this whole unit is about. We have vectors, which is a quantity that has a magnitude, which is that size that we're talking about, but it also has a direction instead of having no direction. Then the magnitude is, the length of the vector. So basically what this means is that you have something that doesn't only have a magnitude of, like, let's say 5 meters again. It also has a angle. So let me not do 90. Let's say it's this much, and the angle, since it's off of this horizontal plane, let's say the angle is like 45 degrees. But it's also 45 degrees northeast. So, and let's say this is also 5 meters. So you would say it's so it's 5 meters, 45 degrees northeast, which would be a vector. So then the components of a vector include the horizontal component, the vertical component. The examples of vectors would be the velocity, since the difference between speed and velocity is that velocity has direction, still in meters per second, but it has direction. Same thing with acceleration, meters per second, except it also has direction, because you can accelerate in different directions. And you have gravity, things can gravitate towards a certain, direction as well. And then same thing with force, you can exert force in a different, in a specific direction. So then the components you have are the horizontal component of the vector, you have the vertical component of the vector, and then you have, when you're using 3 of them, you have the 3D component of the vector. So let's say we start at like this point as the origin, horizontal component, either called X or I. You have this as the horizontal component. Then let's say we go up. That would be the vertical component, either Y or J. And then 3D would be like this. It would be, the 3D component, it's either Z or K. So we have Z or K, Y or J, and then X or I. Okay. So then basically for a vector, the notation is either like a bolded letter or like a letter. Okay, so like I was saying, we have the vector being showed as like a bolded letter or a letter with a line underneath. So basically with the vector, we have 2 forms. We have the column vector form and basically the row vector form. So we have either the XYZ orientation of it. We have XYZ going down vertically, and basically each little, I guess, row in this column is one of the components. So we have I, J, K as well, and before the I, before the J, and the K is we have the numbers. So it would be like 3I, let's say 4J, and like 5K. Doesn't matter. Like that's just where the numbers would go. And then basically with the row vector form, it's typically using the this IJK orientation. Let's say we had it would just be I plus J minus K or something like that in that orientation, but the numbers before the I, J, and the K would be the actual components of the vector. So it would be like negative 3i plus 3j minus 7k. You would have negative 3 as one of the components, 3 is one of the components, and negative 7 as one of the components. So then let's move to a problem. So we're going to find the vectors and magnitudes of vector AB and vector AC. So we're gonna find the length of, we're gonna find the vector and the magnitude. So basically, to help with that, I decided to draw like a little graph and a triangle with it, so we can sort of visualize and I guess conceptualize what it is that we're doing. So the first point I put was, A over here at what about seems like 2, 2, 5. My bad, sorry for the negative. 2, 5, and then we have B over here at 3, negative 2. Then we have C over here at what appears to be 4, 2. So then basically what you need to know is that vector AB is equal to B minus A. So we know what B equals. B equals 3, negative 2. And so you just do 3, negative 2 like you would normally show. And then it's subtracting A. And A, if we look over here, is 2, 5. So we have 2, 5. Sharpie, 2, 5. So then basically with subtracting vectors, you just go straight across like normal subtraction. It's just that this time you have like layers. So first you have 3 minus 2, which is 1. Then you have negative 2 minus 5, which is negative 7. Negative 7. So then here, this would be the vector for AB. And then we're gonna do the same thing with AC. With AC, we're going to look at A. We know basically AC is, we're gonna write it, and let's see if we can fit it over here. AC, we know, is equal to C minus A. Yeah. So then we know what C is. C is 4, 2. I'm gonna subtract A, and A we know is 2, 5. Okay, so then we subtract straight across, we get 2 over negative 3. That's the answer. So these are the two vectors for those two, find the vectors and magnitudes. Those are the two vectors. So then now we're going to find the magnitude. And as mentioned before, the magnitude is the length of the vector. So now we're gonna find the length using this formula, which in your IB formula packet is it's written like this. This is an absolute value in this sense, despite it looking like absolute value because of the lines, but this means magnitude of the vector. It's equal to, basically, this comes from the Pythagorean theorem, but it comes from the square root of each of the components being squared and added to each other. So let's do, basically, let me show this first. So we have first component squared plus the second component squared plus, if you're using a third component, the third component squared, okay? But in our case, we're just using, we're using two components. This is two-dimensional, just x, y, just ij, I guess. So yeah, so now we have the magnitude of, we're gonna do AB first, which you got is 1, negative 7. So magnitude of AB is equal to the square root of, the first quantity is 1, square that, and then plus the second quantity, which is negative 7, gonna square that. So then that ends up equaling 1 plus 49, and that equals the square root of 1 plus 49, which equals the square root of 50. So the square root of 50 would be, I guess, would be our answer for the magnitude of AB. And then let's do the same thing with AC. AC we know is 2, negative 3. So I'm gonna try and fit it over here in this little box I'm gonna make right now. So then AC is 2, negative 3. So we have the magnitude of AC equaling 2, negative 3. So we have the square root of 2 squared plus negative 3 squared. how well you can see that, but yeah. So then we have 4 plus 9, the square root of 4 plus 9 equals the square root of 13. So then, yeah, that's your answer for the magnitude of AC. Yeah. Okay, so we're gonna do another problem, a little bit different. We're gonna show that the points D, E, F with positional vectors 1, negative 2, 3, then negative 2, 3, negative 1, then 4, negative 7, 7, respectively, are collinear. And as we should know, collinear just means that the points are on the same line. So we can just, without even looking at the values, we can just draw the line because we know that these points are going to be on the same line. So D, E, and F, okay? So then basically they're asking us to show that they're collinear, which means that we have to, first we have to find the vectors themselves. So let's find for DE. DE, as we know, you go backwards. If you're trying to find DE, you would just do E minus D. So then we have E equaling negative 2, 3, negative 1. And we're going to subtract that from D by D. So then we have 1, negative 2, 3. And so then you get, let me see, negative 1 minus 1. So you get negative 3, you get 5, and then you get negative 4. Yep. And then, so that's that. And then you have, we're going to do E to F as well. So EF is equal to F minus E. So then you have F respectively, so it's right here. F is equal to 4, negative 7, 7, minus E, and respectively it's right here, so negative 2, 3, and negative 1. So 4 minus negative 2 would be 6, negative 3 minus 3, that's negative 10, and then 7 minus negative 1 is going to be 8. It's going to be 8. So then basically what you have here is you have these two, these two vectors, DE and EF. And we notice that with each of these, if you multiply each of these by negative 2, you get the value of EF. So negative 3 times negative 2, 6, 5 times negative 2, negative 10, negative 4 times negative 2, 8. So then negative 2, so negative 2 is what we call the scalar multiple, which basically just decides how long the direction of the vector is going to go for. So you would have like an arrow here. Let's say this vector is going this long. If you do 2, if the scalar multiple is 2, it would be double that. So this would just be like 1n, and let's say about here is like 2n. This right here is the scalar multiple. So in this case, the scalar multiple is negative 2. So to show that, it's just, you would write EF is equal to negative 2 DE. Yeah. So then now we're going to do the vector equation, just to show that out and help our understanding and show where this scalar multiple applies. So basically it's, the vector is equal to what you call a positional vector. Let's say X, Y, Z. And it's plus the scalar multiple times the directional vector. So we know what the scalar multiple is, but it's normally shown as a T, but it can also be shown as this little weird symbol right here. Looks like a backwards H. And then you have the directional vector right here. So that's the equation. Okay, then we have the scalar product, and the scalar product is, it combines two vectors and results in a scalar. So let's just try and do this now, because the formula right now is, it looks like a multiplication sign, but it's just showing the scalar product, or it's also called the dot product. But yeah, this is what it is. So basically, this is equal to basically the components of each of the vectors. They're multiplying by each other, and then you're adding each of those newfound components, and it helps you get one scalar, like it says right over here. So it's V1, W1, V plus V2, W2, and then V3, W3 if you have a third one. So we're gonna try this. So we're gonna try this vector 4, 7, 2, and 9, 8, 11. So basically you have 4 times 9 plus, so this is the first line, 7 times 8 would be the second, 7 times 8 plus, then the last line, 2 times 11, which is over here. So then you add these, this would be 36, 56, 22. So then you add these all together, 100, you get 114. So then, yeah, this would be your dot product. It took these two vectors over here, and through a little process, it made one scalar. All right, so yeah, let me write the equation again down here. The dot product is equal to the components being multiplied together. The first set of components, and then etc. You gotta add them with the rest, as shown over here, and what we did over here. So then, so then another problem, the last problem, oh yeah, I'm sorry, this is the problem that we just did. So I just put it over here instead of over here. So then lastly, I'm gonna say the formula for the angle between two vectors. This one's a little more self-explanatory because it's just the angle between two vectors. But yeah, so the formula is basically you have cosine theta, this thing right here, theta, is equal to the dot product that we just learned about, divided by the magnitude of those two little values. So you have magnitude of V times the magnitude of, this one's not a dot product, so actually ignore this, it might confuse you. So there's the magnitudes multiplied, and then on top of that you have the dot product or scalar product. So then, yeah, we're gonna start. We already know what this is because we just did it. We're gonna just write right away 114 over, we haven't found this yet. But yeah, so if you do that, let's say the first one you have 4, 7, 2. So 4 squared in this little formula, 4 squared plus 7 squared plus 2 squared. It ends up equaling, once you solve it, it ends up equaling the square root of 69. And then for that would be for V. Then for W, we end up getting, we use, since it's 9, 8, 11, you have the square root of 9 squared plus 8 squared plus 11 squared. And if you solve that, it ends up being the square root of 266. So then you have the square root of 69 times the square root of 266. And this equals cosine theta. So then once you do just this part and you put it in your calculator, you get 0.84. 0.84 is equal to cosine theta, all right? And then basically we can use we can move it around a little bit and we're trying to find theta. We're trying to find this angle between the two vectors. So just take theta and we set it equal to the inverse cosine of this x value. So then 0.84. And when you plug that in your calculator, you end up getting 32.86 as your answer. Okay, so this is the homework I'm leaving you off with, and thank you for watching the video.